Alright, hell yeah. So we're going to do a torsion proof. And I'm going to try to do something I've never done, is make a faster video. Now, I probably just jinxed myself even saying that. But what I'm going to do is try to do this proof like I was on a desert island. You know what I mean? I'm going to do it my way. And hopefully it's simple. So torsion is where we have a shaft, and we're going to tweak on one end and tweak on the other. You know what I mean? So we're going to do this. All these proofs from a material mechanic perspective is like we start by something. Alright, hell yeah. Sorry about that. But yeah, all proofs in material mechanics start with like geometry and then like a change in geometry. So if we were talking about tensioning something, we would have a change in geometry, it lengthens, and that's important. And then we relate that to like the force you applied. So when it comes to torsion, we're going to be shearing. So that little square, after we torque it, is going to turn into a diamond. And so what direction? I just like to draw the diamond this way. So there you go. The other aspect of this diamond that should be relatable is that the diamond just goes this way. You know what I mean? It doesn't go in the classic oblique diamond shape like that. We're talking just a diamond shape that goes, it used to be a square and now it's like that. So we have vertical walls. That's the first important part. Because you can do this from experiment, and what we'll notice is that all these disks of molecules, remain a disk of molecules. But when we torque on something, we get a twisting. If I drew a straight line, it would. If I drew a straight line on this and then twisted it, maybe I would get it to twist this way. So, sorry, in this one, I twisted it this way, and then in this one, I twisted it that way and that way. But anyway, you can torque things any direction. Okay, so this little diagram shows that we are shearing. We're not having any tensile or compressive strengths, and it's a disc of, I like to think of things as like molecules down to the actual molecular level. And to make things simpler for our shaft, I'm going to make it hollow, and I'm going to make it one molecule thick. So this is a hollow shaft, one molecule thick. Molecules are steel, like iron molecules. And so what we see is I have two of these discs of molecules. One is maybe going up that direction and the other is going down. So this is the nuts and bolts from the material mechanics perspective. Like we don't have two molecules doing this in tension or compression. What we have is and it's nonsensical. I'm going to say this because this is good, and now my videos are going to get longer. Shoot. But anyway, it's good to do. If I have two molecules and I do one up and the other down, this is just going to spin. If these are forces, it's just going to spin. So when we talk about shear, you at least need 4 molecules, and typically you'll just do a little square. And this square can be an infinitesimal. So down to what makes sense from a quantum perspective or a non-quantum perspective is at least chisel out 4 molecules. That it doesn't make sense to chisel out a proportion of a molecule. And especially since this can be a differential element. It doesn't have to be a differential element. It can just be some sort of element. It's 3-dimensional. If these are 4 little molecules, obviously they got some dimension. So we do have that. But the nuts and bolts is that, hey, I'm going to do that and that. But again, even though that I have 4, it doesn't make it any different than this. This thing is just going to spin. And so if I put a force up and a force down, so that's the first thing. I need something to counter this spin. And then so I'm going to put a force this way and a force that way. And the other thing from, I don't know if this, molecules have electrostatic forces, or you have some sort of interaction between molecules, they have to be through the center. You know what I mean? That you can't just take a molecule and then put a force on the side. Hell no. So even if you get down to 4, you're still taking these forces through the centers of the molecules. You know what I mean? So even if I had a steel bar and I put some sort of force right there and there, you know what I mean? Maybe, I don't know. Like if this is a solid steel bar, well, maybe I just welded a thin plate of steel right there, a thin plate of steel right there. In this, I still have a line of molecules where I'm applying the force and a line of molecules where I'm applying the force. When you're applying force, you're still applying it through the molecules. And if I'm applying this force on this face, they have to be through the molecules. And then, sure, there's going to be adjacent layer of molecules. So this molecules will go down, these resist, and I get the diamond shape to form. So hell yeah, in this, these two go up, those go that way. But again, these go this way and that way. So you can represent this 2 different ways. You can start with your square. You can say that this went up, so I'm just going to do that. I can say that I'm going to fix this side. But anyway, you could either draw your diamond like that, or you could say, hey, this face went that way. And so you could draw your... I'm not going to explain how the hell to draw these, but you can kind of just see what I do and then complete the square. So we got booyah, 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 booyah. Got your oblique. So it could do that. But there is no difference between this, and I don't think there's any difference. Because what we're saying is like we're just taking this and then rolling it back that angle. And then so if I roll that back straight, this angle gets bigger. This goes flat. It's the only thing right here is this is just the angle divided by 2. We're going to do this as the angle. That sucks, but whatever. That's an angle. Here is just the angle. This is the angle divided by 2, and we're additive. This is the angle. So that's what we have here. So that's that in a nutshell. But to shear anything, you have to have not only 2 forces to do the shearing, but to make sure it's not just spinning, you have to have 2 other forces that are balancing that. Alright, and so I think this is cool. So from the material mechanics perspective, I can work one way or the other. I can say if I have 4 molecules, to actually get these things to rip apart, I have to apply these, and if I want them to get them to rip apart like right there, I have to apply these forces, you know, this way. And if I do that, I have to apply the counterbalance forces that way, because I'm generating a twisting, and I have to, you know, make sure it doesn't spin. And so I require all these forces. But if I do apply these forces, hell yeah, I can separate. Maybe I can separate those 2 slices of molecules. Like, and if I do that, I have broken these bonds. Same thing with the shaft. Like, wouldn't it make sense if these molecules slide past each other a certain amount? They break. And so that's the hardest thing about material mechanics. I just made a video on, I don't know if I'll post this one first. But what I like to think of when it comes to material mechanics is I hand you some material and I say this has a strength or a force that you can put on it. You know what I mean? So here's your block of material. With that, there's 2 properties. You can either put this max force, and then if you do put the max force, let's say in tension, you're going to get a max change in length. Cool. So that's where we do tension and compression. How do we relate this to shear? Because even if you do this, and what does this max mean? To me, this max just means the top of the linear range, which is where you get all your strength. If we go past that, I'm just going to pretend it breaks and kills people. Even though a lot of materials go into a plastic range, they're not just going to break like glass. But still, once it gets to the top of that linear range, mentally, I think it breaks like glass. That's how I think as an engineer you could keep people from dying, and to make some emphasis out of that. At the top of that range, also, if you just let go of the forces, all the molecules go back to the original shape. So if we have this idea that we're tweaking a shaft, sure, we're going to get these molecules to slide past each other. They didn't break yet. And we can do this to a max. Like we're using this property of just like visually. In this one, we were looking at change in length. In this one, we were looking at an angle that forms when we're doing this. And there's going to be a max angle. For steel, it's 0.004 radians. This, for steel, the change in length is 0.002. And this is going to be change in length for unit length. Radians is very similar because I'm going to have some sort of distance here. And if this is the angle in radians, radians times this radius is this height that gets formed. You know what I mean? So you do have that, which is very similar, because 0.004, this is a change in length divided by initial length. This 0.004 is still this change in height divided by this, I'm just going to call it d, change in just initial distance. How about that? This initial distance. So we have change in height, initial distance. These two things are synonymous because this angle is real small, and we can neglect a sine or a tangent. In this case, a tangent to relate those two sides. All right, hell yeah. So this is still just the pregame, but it's really good. I don't mind going over, what is this called, shear as much as possible, because I think it's bizarre, the fact that, I mean, you're trying to get molecules to do this. You can only put the force through the molecules. If you do that, it would spin, so you have to have two other forces. Like, you know, at the end of the day, like, these are just a resultant force at diagonals. And when you do this, you actually pick up two other forces this way. You know what I mean? So that's a conundrum. But what happens is, like, hell yeah. You know what I mean? So those four forces can just be switched to those. So now you're lengthening these and you're compressing these. And then so we actually do go back to a fundamental perspective. It's just like, and when we do this, what do we get? This is going to be a 1.4F. And then this is going to be a 1.4F. I think. You know what I mean? Don't quote me on that. But it's because the additive nature, and we might as well try that. So let's see if this works. So when we have shear, we're going to do an up, a down, a right, and a left. I'm going to say this is a value of 1. And I'm going to come here and say this has so we're gonna take that one up, this one over, and then we're going to have a resultant right there. I don't know if that's actually how I want to do this. Oh yeah, no, that's not how I want to do it. I think this is a puzzle, man. I mean, but if you're not just fully versed in shear, then this proof isn't going to be very good at all. You know what I mean? So this is a very good one to do. So I'm going to put this up, this down, and then these over. And I'm just going to focus on one angle at a time. But I want these to be like this. So if this is the resultant, I want to have it, you know, in two different locations. So I'm going to say, from there to there, I'm going to go this way. I'm going to put open arrows on them. That's kind of useful. Just to be like, hey, this is the resultant, and this is this arrow plus this arrow. Hell yeah. So, you know what I mean? We're doing it, right? And we're going to go this way and this way. Same thing. And this is a very simple, you know what I mean? Simple thing that we can do. I don't know if and you can go three different ways. I can go this way and this way. You know what I mean? So we'll see which one. And even here, I could have gone this way and this way. Which arrows? I mean, that kind of makes it a little bit. We don't have to get too crazy. But let's go this way. So we're going to go that way, and then we're going to go this way. Hell yeah! So we're going to go this way and that way. Cool. So if this was a force of 1, or just F, so this arrow was F, this arrow is F, this arrow is F, this arrow is F. These arrows are the square root of 2, just from geometry. You know what I mean? They're not just half. They're 0.7, square root 2. And I don't have that right. They're square root 2 divided by 2, which is 1.414, divided by 2, which is 0.707. So there's 70.7% of 1. So there you go, divided by 2. And then square root 2 divided by 2, hell yeah, we'll do some math. You know what I mean? Divide top and bottom by the square root 2, so we're unrationalizing. We're derationalizing the denominator. But anyway, we got 2 divided by 2 square root 2. 2's cancel. And this is the same. 1 divided by the square root 2 is the same thing as that. So hell yeah. So this is 1 and this is 1 divided by the square root 2. I think you get it. So cool. Let's add up the arrows that we have. We have 2 of them going in this direction. So those are going to add. And since they're both 0.707, we're going to have an arrow that's the square root of 2f. You know what I mean? 1.4, right? 1.414. Hell yeah. So that's just those 2 arrows. That's just those 2 arrows. Then we're going to come down here. We're going to have the same thing there. So we have 1.414f, which is square root 2f. Hell yeah. And those are just those 2 arrows. So now we got these 2. So we're going to put this one in compression. So we have square root 2f, and then this one in compression. Both those add up to square root 2f. But even that, man, that is a tricky diagram that I don't even have, you know what I mean, down from memory. I kind of just had to guess at it, and then we did it. So that's what's going on when we're shearing something. If I am applying kind of a shear force, I feel like, you can do this with chalk and stuff. You know what I mean, ripping chalk into, and maybe I'll do that. Alright, hell yeah. And to rip this chalk in two, gripping it here and here, it feels like I'm just putting a force that way. But I mean, just like tensioning, if I pull a force this way, I have to pull an equal and opposite force to rip it apart. You know what I mean? And that brings it back to what we were talking about. If I just take this and put a force this way, it's just going to go that way. Nothing's going to happen. Same thing as if I grip here and do an upward force and a downward force, if that's all I do, guess what happens? Hey, look at that, it just spins. Nothing happens. So to actually get this thing to shear, I got to put an upward force, a downward force, and then and let's draw a picture just so we can visually see this. Because I don't think shear is intuitive at all. So yes, I'm going to put an upward force, a downward force, and then this is causing a moment that way. See how this is causing a moment that way? I have to balance it with a moment the other way. And the only other two faces I can put stuff on is right there and there. And so I need to have a force that direction and a force that direction. I would memorize the direction of these forces from that. Pick two, you know what I mean, the ones that are actually doing the visual thing that you're thinking it's doing, and then see what moment it generates, that arrow, and then make sure to balance it, and then, you know, put the arrows on the opposite face. I would not get into the, I don't get into the idea that these just face each other. I think that's a little bit lazy. And so, yes, I will throw shade on that. Cool. So, and then when we have this, these two arrows apply now. So I'm going to go up, down, but that also means that I have to, let's see what I have to do. Oh yes, because if I just did this, I have to resist that. So I have to, so if this is the torque I'm applying, this arrow, I have to, apply this torque. And I do that by, yes, I feel my finger pulling that way when I do that. Yes. And so this is kind of interesting. When I just do this, I feel this finger kind of pushing that way with friction. And also I feel this part of my thumb pushing that way. And it's so interesting, and it's so almost cheesy that it feels like you're just ripping it apart at a 45. Even though you're holding it like this, it's almost difficult to shear it in like a pure sense. I mean, you are doing exactly this, but then you're also going back to the picture, is that at a 45 degree angle, you know, if you actually made this element at a 45, you're actually doing this, and then compressing in. And then so if I do this, hell yeah, I can totally feel that tension at a 45, and that's even what you can kind of see on camera is just, well, I'm just pulling at a 45. But I'm also, now I feel even this finger and this finger pushing in on those molecules as well. So it's just so interesting that pure shear is just tension and compression. So let's do it and then talk about it. Hell yeah. And in this, I think what happens, especially with tension, I'm going to explain it like this. I still haven't came up with a very good way. I don't know where that third piece of chalk went. Here it is. But yeah, I get 3 pieces of chalk, and I think this actually has a really simplistic explanation. And I could do a demonstration on this, and I really want to. Fishing line has like a breaking strength that's real low. So what I would do is I would take like, almost 6 to 8, lengths of fishing line, and then I would connect something heavy that I could kind of add to. I could like add mass to it, whether like filling it up with liquid or water. But what I would do is, and the more strings, the worse you would do. I would do like maybe 4, but you get it. No, you don't get it yet. 1, 2, 3, 4, 5, 6, 7. I have 7 strings, and let's say they can each take 10 pounds. So I could take 70 pounds. At 70 pounds, this thing's going to break. So what I'm going to do is I'm going to load it to 69 pounds. Cool, so we can handle that. That's handleable. And then I'm just going to, with some scissors, cut one of these. So it goes away. What do you think's going to happen? Well, every string is going to break. So the instant I hit one string, all the other ones are higher than their breaking strength at that instant and get shocked into being higher. And then so theoretically they all break. So I think that's what's happening. And I can't tell you anymore. But I think when we're doing this, one face shears. And why doesn't it just shear and then why does it double shear? Well, it's because I don't know, and that's a horrible explanation, but I think that is an analogy that is kind of what's going on. The second one string gets broke, all the load is too much for all the other strings that are trying to hold up the system, and they break as well. So you get 3 breaks there. Cool. So we're going to talk about that, but I guess we're also going to do what torsion does, is it shears things, and what we're going to find from our equation, and back to our little shear diagram. No, let's talk about this and then shear that thing. So when we have shear, we got 4 molecules, and we can make the molecules go into this diamond shape. And again, from a material mechanics perspective, I can do this quite a bit, and then let go, and all the molecules go back to the original location. But at a certain point where I either put too much force here and here, and if I do apply this force, if I apply that force, these have to be equal. So every time you do shear, you just have to. If these were not equal, the whole thing would start to spin. So it's a very good demonstration to show these forces are mandatory, else you just have something spinning and go take a dynamics course. Okay. Oh, hell yeah. Now I understand why I'm hitting a brick wall. Because back to these 2 molecules, I can put a force on them, and I know exactly what's going on. Because if I have a 1-inch steel bar, I can put 58,000 pounds of tension. You know what I mean? I just know that. It's just the fact that when we shear things, we get a weird geometry to happen, and then what? You know what I mean? And then even here, every face of this, if I take 2 layers, I mean, there's still just a molecules of square. It's a square molecule that's 1 molecule width thick, and then there's another one next to it. And each of those layers can hold resistance of 58,000 pounds. Now, there's less than a mole of molecules in a slice of 1 inch, I'm sure. Well, obviously, that's an obvious sure, but I mean, there's hell of a ton of molecules. Anyway, each 2 iron molecules can still resist a force, and once you get to that max force, breakage, right? So what's happening with shear? That's what we want to explore. Is, well, it should be very simple. It's like these 2 are just like these 2 molecules. They can only go so far apart before we get breakage. Cool. Well, when we tweak this in this diamond shape, they did get farther apart. See that? You know what I mean? These 2 are getting farther apart. These 2 are crunching together. The cool thing about steel, and I'm just using steel for this proof, visually and mentally, is that it has the same properties in compression. It can only take 58,000 pounds per square inch in compression as it can take in tension. So, cool. When I apply one force, I have to apply the opposite force, and then I have to apply the forces to keep it from rotating. We just said that it's going to be a multiple of 1.4. So I'm already taking these molecules. So now we'll draw that diamond shape one more time. I'm taking these molecules, applying a 1.4 F on those 2 and a 1.4 F on those 2. So cool. So and then this is the deal with shear. It's just like usually you're just talking about this number. This one number is the shear force, like this, and they would use the term V. So I can do that. Just takes a little bit. So I can put a V here, a V there, a V there, a V there. These V's are the same thing as these F's. I like to do F. I mean, I chose to do F because half of America will know what the hell you're talking about. All the engineers will know what you're talking about. But, I mean, the majority of people, they're not going to know the letter V is a force. But anyway, and we're just trying to make it as simple as possible. Cool. And so, yeah, so this is the force. But if I have this as my shear force, I have to have the opposite. But that's similar to having a steel bar and putting a force here. Sure, if this is the force trying to rip it apart, I have to have an equal force. That just makes sense. But with the shear, you have to have those additional 2. And that just doesn't get stressed enough of where they come from and why. It keeps it from just rotating, right? But because they're there, they actually boost up. If I'm just saying this is the value of force that I'm trying to use to shear this piece of chalk, or a bolt or whatever, I'm getting extra because of the geometry, because I have to brace it and apply those extra forces. So I get this 1.4 on 2. You know what I mean? So there you go. So there, in a nutshell, is if I'm applying this a force, the chosen force on 2 molecules, I get something related to 58,000 pounds. You know what I mean? If I just stack these molecules and, put 2 slices of them in a bar. But what I have is these 2 same molecules, you know what I mean? And I think it's probably irrelevant, with their starting distances, but it could be relevant. But anyway, so I have these 2 molecules, and I'm putting a 1.4 F on them. On just these. Let's just analyze these from a shear perspective. Well, and then I'm saying this is just F. I'm starting with this value F that I'm using to shear some molecules. When I do that, I get a 1.4 on 2, and then I also get a crunching in of a 1.4 F on the other 2. And I can take both of those systems. I can say these are an independent system that are getting 1.4 F, and then these are, and then these ones, the ones that are getting crunched together, I'll just draw them in the same. These are getting 1.4 F. That was kind of fun to say. I'll say it twice, but that's it. One more time, 1.4 F. All right, so hell yeah. So crunched in, and then both of these were from a starting value of just F. I put an input in of F, and then somehow I get this, like obviously from that geometry, because we need it, and it has to come from somewhere. You got to apply it too. Just like over here, if I'm trying to rip this apart, sure, one person can pull F, but someone else has to pull F on this bar. Cool. And then to shear something, you need 4. Honestly, this should be a classroom demonstration. I've done it with the balloon. It works so good. And I think, because my voice is about done, I think this is kind of where we're, like, it's so hard for me to get anywhere into the deep proofs, you know what I mean? Because the fundamentals, like, this will change your life, man. Because if you could do all the proofs in the book, and if you don't have an understanding of where the shear comes from, and then I always like go double down on it to make it, you know, just crispy. But hell yeah, so we're doing it. I mean, we're there. So cool. Input of, I don't know why I'm just saying that 10 times, but yes, this input number, and we're getting a 1.4. So obviously this is going to fail way easier. Does that make sense? Like if I'm putting an input of F, it's going to take this value of 58,000. If I'm putting that same input of F, so this is synonymous with 2 molecules inputting F. When I input F, I'm ripping apart 2 molecules with F. This, when I input F, I'm ripping apart 2 molecules with 1.4 F. How the hell? I mean, just assume, okay. So then this thing's going to rip apart way easier. And when it comes to here, what's this? This is actually pounds per inch squared, because this is the strength, or sigma. It's the PSI, excuse me, that can take in tension. And this value is going to be the same for any chunk of steel, any dimension that I give you. As long as it's steel, it's going to obey this when you pull it in tension or compression. Cool. So, and then what is the inverse of square root 2? That's 0.7. Now this isn't quite the story, because you actually do get Alright, hell yeah. No, I will end with this video on this, because this, I don't think this is anywhere. I swear, this is like one of those hidden gems that I've actually never done this. This is like the cleanest I've ever done this. And I was always wondering why, when it came to steel, you get this ratio of 0.707, or I mean, you get a 0.54. You know what I mean? 54%. So if I'm shearing something, or if I have a bolt, if this is a steel bolt, and it requires 1,000 pounds to rip it apart, it's only going to require 540 pounds to shear it. So again, a bolt is going to take 1,000 pounds to pull this way, pull opposite 1,000 pounds this way. If I wanted to shear this bolt, it's going to take 540 pounds this way, 540 pounds this way. Obviously, those other forces apply. I'm putting friction tension with, you know, like in those other directions. But it's only going to take that because you get this multiple. But even here, if I just did this 1.4, if I said 1.4 F is equal to, you know what I mean, I want this to equal 1. I want this to be the max, and so what I would just do is it would just be 1 divided by square root 2, which is 0.707. And I swear I've done it with Poisson's ratio, where I get like even worse, 0.78. But no, that's not what's going on. So Poisson's ratio says if I'm just pulling those two apart, you know, with 1.4 F, and I can only have this value be 1. You know what I mean? So it's just like 1.4 times what makes this value 1. I can only pull these apart as 1, just like over here. I can only pull apart 2 molecules with 1 F in tension. And when I do this shear, I'm ripping these apart in tension and pushing these to their max in compression. But these values can only be 1F. And then so it appears that it's just 1 divided by the square root 2, and F can only be 0.707 or 70%. And then I don't know if I just messed up Poisson's ratio, but now I got it right on this one. It's if Poisson's ratio, or Poisson's effect says if I do pull on this, well, we'll do it the opposite way. Let's just take these two molecules. I can only apply a tension of so much, okay? Or a change in length in so much. Those are the two principles of material mechanics. If I push in this way on these two molecules, it's essentially pushing in on the system, but it makes these molecules, push out by a ratio of 30%. So it's not a 1-to-1, you know what I mean? But if I push in with this force, it's causing these starting positions to be farther apart, and that's inducing tension. And then so you can either think of it as like these two molecules can only get a certain distance apart, but I've already robbed 30% of that distance. So I only have the remaining 0.7% of the distance to go. So what that says is that, and so here's the equation. I'm going to have this value, so I'm going to have the square root 2f. That's going to be, that part's this. Square root 2f has to equal 1, but because I'm compressing these in, I'm going to have the square root 2f, and then 30% of that is adding to the tension. It's like if I'm pushing in this way, it's like someone else is pulling this way, just 30% of that. That's the other way to look at it. So sorry if I'm just kind of messing up making it juicy. But anyway, so here's the equation, which goes to f square root 2 plus 0.3 square root 2 is equal to 1, where f is just 1 divided by the square root 2, 1 plus Poisson's. And if we do this, 1 divided by the square root 2, 1 plus 0.3. Oh, why didn't that work? Oh, sorry. I probably did something wrong. Yeah, that needs to be the square root 2. Sorry about that. Oh, let's just start over. So I'm going to have the square root 2 times 1 plus 0.3. Invert that. Alright, hell yeah. Sorry about that. My camera cut out, but this equation comes out to 0.54, and that's the percentage, or 54.4% of the strength that you would get in shear. And I think where I was messing this equation up is I was just starting with a force of 1. I was saying if I start with a force of 1 in this direction, I'm also having a force of 1 in compression, and I'm going to have 30% of that, and that has to equal, I don't know how I was maybe messing that up. Maybe that has to equal 1, and I was getting 1 divided by 1.3. Yeah, I think I was getting that. I was getting f of 0.769, or 77%. But if I take the 77% of what? The square root 2 divided by 2 times 0.7, 70% of that, that's where you get that 0.54. So hell yeah. So that's where I was messing up, is that we're already, juicing this thing out where we're saying we're starting with a force of F. Man, sorry if that was just the first time I've actually got that right, so I'm just going to kind of move on from this. Alright, hell yeah. I have a hard time just kind of moving on, but that was a really good place to get hung up. So I don't know how far I'll get on this, but we have these molecules. I'm still envisioning. I think the easiest thing for me to envision is a shaft that is hollow and is made up of iron atoms that have a thickness of just one molecule. So I can see exactly what's going on when I twist. is that those 4 molecules right there are making this diamond shape. And then let's talk about the material mechanics perspective. If I put any torque or force, you know what I mean? So I'm not thinking of this as torque yet. I'm just saying, well, I can envision twisting this shaft and then those molecules sliding past each other, or twisting and torquing out. And so to do that, if I have 4 molecules and I get them to make a diamond shape, it requires a force, those 4 forces that we were just talking about. Cool. The other thing about material mechanics is, well, there's 2 ways to look at this. I can either put a max force, and I would know that max force because I would know how many molecules I'm dealing with. And in here, we don't say, hey, if I'm pulling a bar apart, I don't say, hey, I'm just dealing with 2 molecules. I say that these molecules have some sort of surface area, and then so if I have a 1-inch bar, you know, I take 2 discs, you know, of molecules up against 2 other discs, and those are going to separate. So this, in a torsion, these are the circular discs. They're made of molecules. Ours are just hollow. And we're not pulling ours apart like this. We're shearing them past each other. But that still requires a force. And that force max, oh, that's where I was going with it. It's based on the number of molecules that we're using, but we don't say it like that. We just say the molecules have a surface area. So if I'm making a steel bar on a cut surface, I can count up the number of molecules, and then on the other end surface of the bar, I can count up the same number of molecules. Those molecules will touch and interact, and that's what's providing that strength. And we say then, you know, the number of molecules is just related to the area. So you have to have some way to relate it, and that's what we use. Same thing here in shear. I'm not saying that I just have 4 molecules. I say these molecules have area. But now I want to know what area I'm using, and it's this is the face that they're going to shear across, so I'm going to say it's the area in between those 2. That is the area that I'm talking about. And in this 4-pack, I get twice the area, you know what I mean? But we hopefully talked about how I am, well, let's see. Oh man, I thought that was going to mess with my calculations that I did with that 54%, but it's not. It's just, yes, in this, fundamentally, you know, if I break it down to 4 molecules, it has twice the area. And so if I try to relate this to tension, it's like a bar in tension that has, you know, 2 times the area. And so if I'm equivocating, you know, 2 molecules to be a max force of 58,000 pounds, or whatever, or a PSI, or just force in pounds, and I'm saying this would be like a 1-inch by 1-inch bar. Then if I had a 2-inch bar, or a 2-inch area on a bar, I could get twice 58,000. I could get 116,000 pounds out of this bar. And so, so if I'm trying to compare apples and apples, I would compare this bar to this, and then so my input force would be 1,100. And so this is the force to break this bar. Let's say 116,000 pounds. Cool, because it's a 2-inch bar. Here is a surface area of 2 inches. And we want to shear this apart, and I want to know the force that is required to do that. And so let's go through that math. I think that would be good. So still, I'm going to take the diamond shape, have my, oof. Let me redo this. Alright, so I have the 4 molecules that are like this. I want to shear them up like this into that diamond shape. I see that these are, and that requires all 4 forces. I don't want to write them again. I'm going to get a square root 2f, a square root 2f, and then the compression's the same. I don't want to write those again. And let's see. Yeah, I don't know if this is going to work out from just kind of my... Because I've actually never seen it done this way. Alright, hell yeah. I think the one thing that I'm messing up, even from that original thing, I mean, it's still getting the right answer, that 54%. But it's trying to treat this like it's twice the area. I think that is the mistake. I think calling this a unit area of 1 inch squared, or just kind of a unit area, makes it play out. But calling this a unit area and then saying it's 4 individual things, and then these 2 get pulled apart separately that only have an area of a half, that I think is a wrong assumption. And so yeah, so that's where trying to say these are just an area of a half, where this is an area of 1, you know what I mean, or vice versa, or whatever I was trying to do. I think that is an error. But yeah, that's interesting. That's where it would be so fascinating to take a higher level course to see exactly what's happening. At molecular levels, it would be very useful, just for better fundamental understanding of what's going on. Alright, hell yeah. I think I found a remedy. I would call this, I would represent a steel bar as 4 molecules, and I would still call this a representative of a unit area. Like this area is 1, or just A, and then this area is the same because it's those 2. You know what I mean? It's a cross-sectional of 2 molecules. This is a cross-sectional area of 2 molecules. So both of those areas are now the same. I'm going to say this just takes some sort of force, like the 58,000 psi, because that's what it requires to pull apart. These, any 2 or any surface area also, or just any molecules in general, take 58,000 to pull apart. And what we find is, yeah, I think that gets us closer. Yes, and then instead of doing the diamond shape where we do it like this, I think it is appropriate to just do a full rotation of the 4 molecules we're trying to represent, and then just pulling them apart at that 45 and then crunching them in. But not trying to change, not trying to do this and just pretend that it's just 2 molecules getting tensioned and 2 molecules getting compressed. No, I think we need to stick with that it's these 2 getting pulled apart from those 2, and then the surface area still stays the same, and it's these 2 crunching into those 2, and the surface area stays the same. So that's the mistake that I was trying to, that's the mistake that I was making. I think with this, and like I said, I've never done this before, but it was the first time I ever got that 54%. And I don't even know why there's no proof in the book about that 54%. Or maybe I'm just missing it, but I don't think there's any very good proof about that 54% popping up. And that 54% is regardless of material. It's just the fact that you're getting all that leverage from the 4 forces. So hell yeah. So that was exhausting. But I think I have to be done for this proof. What happens for the torsion proof is that molecules can only get tweaked a certain amount before they reach their max. And that's the linear range. The second they get tweaked out, if you go farther, then they get plastic and they'll stay that way. They're not, I mean, if you tweak them out like this distance of 3, like let's say you can go a distance of 2 and then let go, and then all the molecules go back to original shape. That's kind of the fundamentals of material mechanics. This is the linear range. Let go and they go back magically to the identical location. So this was a distance of 2, goes back. Let's go a distance of 3. So just a little bit more, 3. I went into the plastic zone. So if I let go of the force, it's going to go back 2, but then be plastically deformed by 1. So that's what's happening. If it can go 2 magically, linearly, then if I go 5, then I'm just going to go back 2, and it's going to be deformed at a distance of 3. You know what I mean? Just given general parameters for that. Okay, so there is a max that these molecules can go. We relate that max from the angle. And then for steel, this angle is 0.004. And when we, just like we tension something, a steel bar, we have slice after slice after slice of those facing molecules. I mean, we have a slice of molecules, a slice of molecules, and then just on repeat, that makes up a steel bar. Each of those slices can and does and has those molecular interactions to hold that 58,000 pounds if it's a 1-inch square bar. The same thing happens with torsion. When I'm twisting on one end of the bar and the other end twists, every slice of these molecules has to do the same thing as the next slice. They're like these molecules are holding that that angle. That angle is forming in 2 slices. So what happens is these 2 slices, let's say it's the first 2 slices over here, get tweaked, but then this new slice was onto another slice which is getting tweaked. This new slice is onto that, and then so we have this torsion of the bar. We have a helical. If I drew a straight line across the bar, after torquing it on both sides, every slice is going to be shifted because every 2 slices is going to get sheared past one another, and it can resist that shear, and it resists that shear. It's always good to go back how it resists that shear, because when one slides across the other, these 2 molecules are lengthening, and they're getting pulled back. These 2 molecules are getting crunched in, and they're getting pulled the other way. And again, I think what I'm learning from this video is to, when I orient the molecules, I do like this picture, you know, of the diamond shape and then the molecules looking like this, because I can see that these 2 get longer. And there's a proof that the distance between those and the distance between this, well, especially these ones, because that's what we're going to do with chalk. When we do this, these 2 get far. These take tension, and chalk can't take chalk can take this compression all day. It can't take this tension, so that snaps real easily. But it's useful to take these molecules, and if I do tweak them out, to actually rotate this at a 45, and then and so this does go to this diamond shape, but this diamond shape is better represented by putting these 2 molecules there and those 2 molecules there, still having this diamond shape in that direction, but now this is more accurately what's happening. So now I have 2 molecules getting pulled apart very traditionally, and 2 molecules getting pushed together very traditionally. But yeah, let's show this helical. So when I go up like this and down like this, my brother said, "Hell, draw the little, you know, box on here," and then so it's going to get tweaked like that and tweaked like that. To do that, I'm going to have an upward force, a downward force. It's going to create a moment. I need the other forces to balance. Hell yeah. And then so in doing so, let's see. Oh, yep, and then I'm going to draw the 4 molecules. So these two are getting like farther apart. These two are getting crunched in. It's the farther apart ones that are going to break. So the break is going to be like right there, but then it's going to be continuous. So I'm going to get that to form. That is the helical that will form. It's not going to go the other way. It's going to go that way. Hell yeah. And did it go the other way? No, it went that way. Hell yeah. Cool. And like I have to go redo this. Yeah, and you get a cool helical shape to form. And so I swear physics is maddening, where you're just like, I thought we did everything right. Draw the little square, went up, went down, went over, went that way. Molecules, these two got farther apart. They break on those, and that break gets propagated along that plane. And so that's what we see. If you twist it the other way, so this one we twisted it that way. I got plenty of these chalks, so we twisted it this way. We're going to twist it the other way and get the other helical to form. Alright, hell yeah. So this was this way. I'm going to twist the other way. And can we visualize this? When I twist the other way, this is going to crunch in. This is going to stretch out. I'm going to get a helical the other way. So, yeah, I got to twist this way. Hell yeah. So we get that helical to go the other direction. So that's pretty sweet. Isn't that a head game though? You have to like think about it and stuff. Like I do for sure. Alright, hell yeah. So and the interesting thing is I just feel miles of these proofs. Like I really just have to dive into every little detail. But I just still feel miles away from relating how this torque gets related to, I mean, just the value, like, I don't know. Like, what we want to know is just maybe the max torque we can apply. And so we do that by saying, hey, these molecules can only, change an angle by this much. And so this is the easiest one, and this is kind of where I'll end, is that if each of these slices can make this angle, cool, then we can find something. It means that if we drew a straight line and then kind of maxed out the surface, that's why I did the hollow sphere with just the molecules on the surface, because that's where they're getting maxed. If I'm maxing out those surface molecules, I'm going to get that angle to form on each of the slices. And then so this angle remains the same. This is the max. Like this angle is still 0.004. And that's the same throughout the torsion bar. This angle is very, very small. And so we're going to take the length of the bar. This angle is in radians. And so I use the equation radians times radius is something normal, and that's this arc length. So radians times radius is something normal. That's arc length. This 0.004 radians, which is the max angle, which is called the shear strain. So 0.004 radians times the length of whatever bar you're torsioning. 0.004 times that length is this arc length from this angle, which is how much the bar can tweak, and then you can let go, and it's going to be right at that top of that linear range. But if you go any farther, it's going to plastically tweak out. So that's where that max comes from. But I could do this with a steel bar, and all it is a function of its length and this max angle. Shorten the bar, that angle is going to be shorter. If you get a thin wire and the length, that's where you can take like something real thin and just twist it like 3 or 4 times and then let go. All the molecules go back to the same shape. Compared to something that's like round and large diameter, you go to torque it, it's because the angle between those slices can only be so much. Oh, no, it's not a function of the diameter. See, I'm glad I just confused myself. It's just a function of the length. So if I take, and then that gives you the, not to confuse, but that gives you the arc length that you can go. So if I have a given length of, something, and I can have this max angle to form. Cool, I'm going to take that angle times the length, and that's going to give me this arc length. Where if I have something with a high diameter, maybe that arc length is just to there. If I have something that has like where the diameter or the circumference is that distance, then I have that little shaft, and I can twist it all the way once, and then untwist it, and all the molecules go back. Because it's the radians times the length. Radians times radius is the arc length that these molecules, each disk, can make. And so if I have something thinner than that arc length, where the circumference is like 5 times smaller than the actual arc length from this radians times radius, then maybe I can spin that rod 5 times, before those molecules are maxed out. But still, each disk of molecules on the surface is still just doing the same thing every other disk of molecules is doing. You know what I mean? It's still just making that angle. It doesn't know any different, but it is part of something that is narrow in diameter or radius. And so when that angle does form, this arc length forms. And if the circumference is smaller than this arc length, then you're going to have more than one rotation. So there you go. But that's the simplest proof to do. The other ones aren't so bad, but you just have to, what we're going to relate is the, the force that you can apply on molecules. And we do that with the shear stress. And shear is just like tensioning something, has a value of force divided by area, And this is, and for whatever material you're using, this is just a constant value, because we have a force, it's proportional to the area you're using. And so if you double the area, you get to double the force. Just like if I have a 1-inch steel bar, 58,000 pounds, I go to a 1/2 inch area steel bar, I can put 29,000 pounds. But that ratio between force and area remains the same. So this tau is the stress, which is the ratio between force and area. That's the same no matter what material I'm given. And that's what we relate to what's happening at those interactions. And we relate it to, how do we know how many molecules we have? By the surface area. But that's where the integration is not too hard, but you have to figure out, hey, the molecules near the outer surface, like that area is the molecules near the outer surface, and the ones near the outer surface are applying, or it takes a force to tweak them, and if it takes a force to tweak them, that force is a distance away from the center of the circle, and then in a sense it takes a torque to apply a force on those molecules. And so that's why that's why the shaft is torqued, because the torque is a force times a distance, and so and that's creating a moment, axially along here, and that has to be resisted by not only a force, but a force that's a distance away. And then these molecules are a distance away from the center. But if it's a solid shaft, the molecules near the center can't do much at all. So that's where, even if you just take the molecules, like those molecules right there, and just pretend that they're at the end of the shaft, then you get a pretty decent approximation. So anyway, but that's going to be for the second part. I've done enough today, but haven't got... Yeah, it's a bummer that I just can't go from start to finish, or even just get into the actual good stuff. I spend a lot of time on the fundamentals, but it is helpful. because I mean, it makes me feel like a superhero just even kind of knowing stuff that I can't. Some of this stuff I can't find in text, like that 54% crap. I can't find that anywhere in a textbook. Anyway, so hell yeah, I'm gonna be done for tonight. Thanks for joining me. Hell yeah.